This is AQA A-Level Chemistry, and this is the Year 12 Redox topic, and we're now on video 3. In the second part of this topic, we looked at how we can work out oxidation states based on a series of rules. In this video, we're going to look at how we can balance half equations. Again, there are rules to learn that you then must be able to apply. So as always, I'm going to recommend you pause where there are tasks and activities, have a go at them, and then review your answers and check your progress. So, looking at how we can balance half equations and what we can find out from those half equations. And we're going to start with just a little bit of a recap of some of the key ideas. So based on this equation, this reaction between iron 3 chloride and potassium iodide, can we identify the species that has been reduced, oxidized, what the two half equations would be, and what the oxidation states would be? Now, when you've tried it, see how you've done. I'm not going to do it in the order that it's set there, but we can work out that because chlorine is -1 and there are 3 of them, the iron is +3. Whereas on this side, it's only +2. So we can see the oxidation state of the iron, and we can see, because the oxidation state has gone down, that it has been reduced. And if I take a look at the iodide ion going to iodine, it's going from -1 and it's going to 0. So because the oxidation state has gone up, it's oxidation. Now, if we break it down into its ions and we get rid of spectators and break it into its half equations, we end up with Fe3 plus going to Fe2 plus, and that happens by gaining an electron. Then we have iodide ions going on to become iodine by losing an electron. So we can see here that the iron has been reduced because reduction is gain of electrons, and iodide has been oxidized because oxidation is loss of electrons. And I've just got those highlighted on there as well. So another chance to have another go at an example. And we can see here that the iron has gone from +3 to 0, so it's been reduced, whereas the aluminium has gone from 0 to +3. It has been oxidized. And if I do the half equations once again, I have my Fe3 plus gaining 3 electrons, another way of seeing that it's reduction to become Fe, and the aluminium losing 3 electrons to become Al plus 3. But the main thrust of this video is going to be looking at how you can build half equations based on these rules. And the rules never ever change. You don't always need to use all 4 of them, as you will see, but you balance the species that has a variable oxidation state. Now, invariably, that will be the thing that is not hydrogen or oxygen. Then you need to balance any oxygens that are present. You do that by adding waters. Then you've got to balance any hydrogens that are present, and you do that by adding H plus ions. And finally, you need to balance the charge, and you do that by adding electrons. So you've got to work through systematically every single time. Do I need to do the rule or follow the rule? And if I do, what do I need to write down? So let's take a look at the first example. We've got here iron going to iron 2 plus. Now, rule 1 is to balance the species with the variable oxidation state. We don't need to do it. The Fe goes to Fe. So then we need to balance oxygens by adding water. There are no oxygens. So then we need to balance hydrogens by adding H plus. There are no hydrogens. And finally, we balance the charge by adding electrons. Now, the charge on the left is 0 and on the right is +2, so I need -2 on the right hand side to get us to the same charge on both sides. So let's look at a second example. In sulfuric acid, going to sulfur, rule 1, balance the species with the variable oxidation state. It's already balanced, 1 sulfur, 1 sulfur. Then I need to balance the oxygens by adding water. I've got 4 oxygens, so I need to add 4 waters. I then need to balance my hydrogens. I do that by adding H plus. I've got 8 on the right hand side. I've only got 2 on the left hand side so far, so I need to add 6 more H plus. And finally, I need to balance the charge, and I do that because I've got a +6 charge on the left, a 0 charge on the right, by adding 6 electrons on the left. So it's now a series of examples for you to try. So have a go, pause and review. So in this first example, my variable oxidation state species, copper, there's one of each, don't need to balance. There's no oxygens, there's no hydrogens, so all I need to do is balance the charge by adding electrons. Example number 2. I don't need to balance the species with a variable oxidation state. It's balanced 1 aluminium and 1 aluminium ion. There are no oxygens to balance, there are no hydrogens to balance, so all I need to do is balance the charge by adding 3 electrons on the right. H2O2 and H2O. Well, the species with the variable oxidation state here is actually oxygen. So I'm going to balance that by balancing the 2H2O. So I've now got 2H2O, I've balanced the species with the variable oxidation state. In terms of balancing oxygens, I've now already done that. So I then need to balance the hydrogens. I've got 4 on the right, I've got 2 on the left, so I need 2 H pluses on the left. And I've got 2 H pluses on the left, so I need 2 E minus on the left to counteract that charge. I've now got a 0 charge on the left and a 0 charge on the right overall. 2 more examples for you to try. So in terms of rule 1, the species with a variable oxidation state, manganese, is the same, don't need to balance it. So I need to balance the oxygens. I do that by adding 4 waters on the right hand side. I now need to balance the hydrogens. I do that by adding 8 hydrogens on the left. And my total charge on the left now is +7. And on the right, on the Mn plus 2, it's +2. So I need 5 electrons to balance that charge. And we can see there I have got a total charge of +2 on both sides. So let's move on and look at H2SO4 going to SO2. In terms of the species with a variable oxidation state, it's already balanced. I've got 1S on both sides. I need to balance the oxygens. I do that by adding 2 waters on the right. I now need to balance the hydrogens. I've got 2 on the left, I've got 4 on the right, so I need 2 H pluses added on the left. I now need to balance the charge. I've got +2 on the left, I've got 0 on the right, so I need 2 E minus on the left hand side. 2 more examples to try. Again, in this case, my species with a variable oxidation state is already balanced. So I balance the oxygens by adding 4 waters. I then need to balance the hydrogens. I'm going to do that by adding 6 H plus. That's now 8 on the left, 8 on the right. I then need to balance my charge. 6 plus on the left, 0 on the right. So I need 6 electrons on the left to bring them both to 0. And sulfuric acid again going to H2S. So on this one, my sulfur is already balanced. I need to balance my oxygens by adding 4 H2O. I then need to balance my hydrogens by adding 8 H plus. And finally, I balance the charge by adding 8 E minus. 2 more examples for you to try here. So dichromate 6 to Cr plus 3. Rule 1, balancing the species with a variable oxidation state. You've got 2 CRs here, you've only got 1 there, so we have to consider rule 1. We then balance the oxygens by adding 7 H2O on the right. We balance the hydrogens by adding 14 H plus on the left. And finally, we work out the overall charge. I've got +12 on the left, and I've got +6 on the right. That means I need 6 electrons on the left-hand side. And the final example, HOCl going to Cl2. I need to balance the species with the variable oxidation state, that's chlorine. So I do 2 HOCl. I now need to balance the oxygens, 2 H2O on the right. And I now need to balance the hydrogens. I've got 2 here, I've got 4 here, so I need 2 H plus on the left-hand side. And finally, to balance the charge. So I've got 2 plus on the left, 0 on the right, so I need 2 electrons on the left-hand side to balance them. That brings us to the end of this video. Thank you for listening and goodbye.